Okay, so welcome back. Today we are going to delve a little bit into spectral theory, okay, for linear transformations. This is really a huge topic in linear algebra, and you see its applications throughout mathematics. But we'll see a few things, kind of the start of it today, and I think get to some hopefully cool theorems. Okay? So let me start with an example that we have seen before, okay, when we first defined matrices of linear transformations. So we had the matrix 2, 1, 1, 1 going from R2 to R2. Okay, so this is with respect to the standard basis. Okay, so this is just the linear transformation, which sends this square spanned by the coordinate axes to this parallelogram, which is spanned by 2, 1, and 1, 1. Okay, so this is the point 3, 2. Okay, and then we notice that this linear transformation had two lines which were stabilized. Okay, so the first line passed through the vector v, which was 1 plus square root of 5 over 2, and the second line was spanned by w, which was 1 minus the square root of 5 over 2. Okay. And on the first one, so on v, the transformation sent the vector v to a multiple of itself, so it sent it to 3 plus square root of 5 over 2v, and w, or t of w, was 3 minus square root of 5 over 2 times w. Okay? So now the same linear transformation has this picture where if we look at the line spanned by v, it might look something like this, the line spanned by w. Okay, so v is on here, w is on here. What this linear transformation does is expand, so it stabilizes both the lines, but it expands. This line, it's multiplied by a constant larger than 1, and here the line is contracted. Okay, so multiplied by a constant less than 1. All right, and so in the VW basis, this matrix has a very nice form, which is just the values 3 plus square root of 5 over 2, 0, 0, up 3 minus square root of 5 over 2. Okay, and this was useful if we wanted to figure out the dynamics of the linear transformation. Okay, so in other words, what I mean by that is we want to study t to the n for large n and quantify kind of where all vectors are going. So we want to look at something like t to the n of u, for now u and R2. Okay, so for one thing, this is useful to take nth powers, because if I take the nth power of matrix in diagonal form, I'm just taking the nth power of each individual terms, so it's easy to compute. Okay. The other thing that's nice from this is that since I have one expanding and one contracting direction, what happens is that t to the n u approaches the v line, okay, so the line spanned by v, for all u in R2, except for u in the contracting line. Okay? So if I take some random vector, like here's my u, and I start looking at what happens to high powers of it, well, I'll see it just slowly approaching and actually becoming asymptotic to the line spanned by v. Okay? W, well, it's stabilized. Things just approach the identity, or sorry, the 0. Okay? So on W, things are kind of moving towards 0. Everything else kind of gets sucked into this expanding direction and starts moving towards it. Okay, so we get this kind of, this dynamical picture. If you want to see this, well, how do you know that this is, kind of the dynamics that's going on? Well, notice that if we write U in the VW basis, okay, so U will just be, AB, okay, but this is written in terms of V and W, then T to the N, U, again, written in this basis, well, it's just 3 plus square root of 5 over 2 to the NA, 3 minus square root of 5 over 2 to the NB, okay? But now for any value of B, this is going to 0, okay, in the VW basis. So what this means is that the W direction is appearing less and less, right? So this is shrinking to 0, meaning that if you write a vector as a sum of V and W, then you get that the W term becomes negligible. On the other hand, the V term quickly dominates and becomes essentially the entire story, right? Since this number just becomes huge. So in the long term, vectors kind of get sucked into the V line, and then this transformation is just multiplying them essentially up to a little wiggle room by a power of 3 plus square root of 5 over 2 every time, okay? So let me do another example that we've seen before, okay, which is 2, 1, 1, 2. Again, we worked out this in a homework that this was similar to 3, 0, 0, 1. Okay. In this case, the basis was 1, 1, and 1 minus 1. And again, you'll see that we have these lines which are stabilized. In this case, you get kind of an expansion in this direction. So here terms are getting larger and larger, and in the other direction, this is just staying constant. Okay, so this line is actually honestly fixed under this transformation. The terms aren't also shrinking along it towards 0. Okay, so maybe I'll just, before talking about different behavior, of course you can imagine you can have linear transformations where both things shrink or both directions expand. I'll note here that in both examples, the two stabilized lines are perpendicular, okay? So the way that you calculate that is, well, you look at, the first one is, you're looking at 1 plus square root of 5 times 1 minus square root of 5 plus 2 times 2, okay? And this produces 0. The other case, you're getting just 1 times negative 1, so you're getting 0. Remember, this is perpendicularity is if you have v1 w1 plus v2 w2 equaling 0. Again, I haven't really formally introduced why we're talking about this, but the geometric picture is clear here. Okay, so you have two lines which have kind of various behaviors on them, and in both cases they're orthogonal. So this turns out to not always occur, so not every linear transformation is going to have two orthogonal lines that are stabilized by it. But it's nice enough when it does occur that I wanted to point this out now. Okay, so let me give you an example of linear transformations which don't have these fixed lines. So we've seen both of these before. So one of them is 1n 0, 1. Again, always in standard basis, though it turns out not to matter. So in this case, the x-axis is fixed, right, under this transformation, and the y-axis gets skewed. So I'll just draw this here. So this is the image of the square spanned by the standard coordinate axes. And now it's easy to see that there's no other stabilized line, right? So there's only one line stabilized, namely the x-axis, and every other line through the origin. All right, so again, well, so of course it stabilizes lines that are parallel to the x-axis. We're most interested at this point in vector subspaces, so if I take any line through the origin, it's going to get sent to a different line through the origin. Okay? So that can happen. All right, so there's the shearing behavior. And the other example that we've seen is if you take a rotation matrix. Well, here, there's going to be no line stabilized. Okay? So essentially, if you're working, so you're thinking about R2, and this is a rotation matrix, there's not going to be any line stabilized, so there's no real change of coordinates that will put this matrix into some nice diagonal form, or even some form like this, where there's going to be a fixed vector. Okay? On the other hand, what we're going to see is that working with complex numbers is better here. Okay, so I'm being kind of intentionally vague, but you can imagine a rotation matrix written, if I was just thinking of this as the complex plane now, this would be a 1 by 1 matrix where this z is e to the I theta, okay? And somehow this is a very simple way to represent the matrix. It's in a diagonal form, so thinking about complex matrices can sometimes help us here, and it will help us. Okay, so let me make this all a little bit more precise. So if we have a linear transformation, okay, let's just say t from v to itself is a linear transformation. This will only make sense for vectors, or for transformations which go from the same vector space to itself. Okay, so lambda in F, the field is an eigenvalue of t if there exists some v in v so that t of v is equal to lambda v. You can similarly define this just for a matrix A. Okay, so define for matrix A, and then you're asking about matrix multiplication rather than the linear transformation. It will end up being a lemma that if you have a linear transformation and two matrices which represent that linear transformation in the same basis, then an eigenvalue for one is an eigenvalue for the other. Okay, so every eigenvalue has a corresponding eigenvector or set of eigenvectors. So an eigenvector v, and I'm going to write this in terms of the matrix, just so it's slightly more convenient, is a solution to A minus lambda times the identity matrix x is equal to 0. Right? If I plug in this vector v, then A of v is just exactly lambda v, and that's, so in this case you get 0. So now this is, you can think of it as a new linear transformation, and you're looking at the kernel. Okay, what this says is that the set of eigenvectors for a fixed eigenvalue lambda is a subspace, okay, of V. And you can do this in exactly the same way with transformations. Just take t minus lambda times the identity transformation. That's all that is doing. Okay, and we usually call the set of eigenvalues the spectrum. So I'm going to say the spectrum of t. This is now just a set of real numbers. So it's exactly the lambda, where lambda is an eigenvalue of t. Okay, similarly you can define that for a matrix A. Okay, so now, I mean, the thing is, well, we have a linear transformation, we have this definition. How do you figure out what the eigenvectors are, or what are the eigenvalues? Well, it turns out that it kind of helps first to figure out what the eigenvalues are, and then that helps you figure out the eigenvectors, since you just find the kernel of this transformation. So how do you find eigenvalues? Well, you want to find the lambda so that A minus lambda I is non-invertible. Okay? And as we saw, one way to do this, of course there's other methods, but one way is to show that the determinant of A minus lambda I is equal to 0. Okay? So if you can show that, then you've found an eigenvalue. Okay, so let me give you an example of a 2 by 2 matrix. For one thing, the determinant formula is quite nice, and on the other hand, it turns out to be kind of a cute answer. Okay, so what we're looking to compute is the determinant of A minus lambda B C D minus lambda. Okay, so this is just AD minus A plus D lambda plus lambda squared minus BC. Okay, so we get lambda squared minus A plus D lambda plus AD minus BC. Okay, and we're setting this equal to 0, and you want to solve for lambda. Now, here is just something to know. Well, here you have the usual determinant of the matrix that you started with. Okay, and here you have the trace. Okay, so it turns out with the formula that you get is that lambda is equal to, by quadratic formula, trace plus or minus square root of trace squared minus 4 determinant over 2. Right, and now there's kind of 3 cases for the possible eigenvalues. Okay, well, in this case you could have 2 roots which are distinct. Okay, so this occurs if the trace squared minus 4 determinant is greater than 0. You could also have a multi-root. Okay, and this corresponds to the trace being trace squared minus 4 determinant equaling 0. Or you could have no roots. Okay, so this is where it's less than 0. All right, and we recover our examples here that we've seen before. So this corresponds to having 2 eigenvalues, 1 eigenvalue, and none. So in this case, we can check the 2, 1, 1, 1 matrix. We'll have trace squared minus 4 determinant positive. This has the 1, n, 0, 1. We'll have trace 0, and we saw that there was 1 eigenvalue. And finally, this one has, let's see, it can be cosine, sine, negative sine, cosine. So in this case, trace squared is 4 cosine squared theta. The determinant is cosine squared plus sine squared. Or we could have said this rotation obviously preserves the area of the parallelogram. You're just rotating a parallelogram around the origin, so the determinant has to be 1. In any case, you're getting this expression, which is less than 0 unless theta is equal to a multiple of pi. Okay, and in this case, this is the special case where you have an eigenvalue because either, well, okay, so theta might be 0, in which case this is the identity matrix, so you have an eigenvalue of 1, or theta might be pi, in which case you're flipping, so you're getting an eigenvalue of minus 1. Okay, so let me make a couple remarks here. So the first one, this isn't exactly obvious from the definition of the determinant I gave you, but it happens to be true. So if I look at A minus lambda I, that matrix, and take the determinant, this is equal to a polynomial in the variable lambda of degree n. Okay? So for, so this is for an n by n matrix. All right, so in general, any linear transformation or matrix, I'll just say linear transformation on an n-dimensional vector space will have less than or equal to n eigenvalues. Okay, just by looking at this formula. Okay, or you can also compute it by saying that every eigenvalue should have a corresponding eigenspace. Okay, and there can't be more than n of those. And this is kind of the first case where complex numbers are better for us than real numbers. Okay? Than real numbers. And the reason for that is, well, we can, if we go back to this equation for the eigenvalues, well, even though, and then you have to remember, now this is, if you have a 2 by 2 matrix, this is inducing a linear transformation from C2 to C2, okay? So if we look at that equation, and in general, if you look at a polynomial of degree n, all over the complex numbers, right, polynomials must have roots. And in fact, that that there are n roots, right? There might be some roots that are multiple, right? So that can still occur. But that you can completely factor a polynomial over the complex numbers as a product of linear terms. Okay, some of these, again, might be the same, but this means that if you're looking at kind of this spectral theory for matrices, real matrices are hard to work with because they don't have as many eigenvalues as they should. Complex numbers always do. Okay, so that's something that we're going to use. The second thing that I want to remark on is that if A and B are similar, okay, then A minus lambda I and B minus lambda I are also similar. Okay, so this is easy to check. So if B is equal to SAS inverse, okay, then B minus lambda I is SAS inverse minus lambda, put this here, S lambda I S inverse. This is just S A minus lambda I S inverse. Okay, so distributing out the S inverse and the S. So now, if these are similar matrices, these are similar matrices, what this means is that they have the same determinant. Okay, so the determinant of A minus lambda I is equal to the determinant of B minus lambda I. So in other words, lambda being an eigenvalue is a property of the linear transformation, not the matrix, right? Which we noted earlier. Okay, because now if I take any two bases and write them as matrices write this linear transformation as a matrix with respect to these two different bases, if lambda is an eigenvalue for one basis, it'll be an eigenvalue for the other basis. Okay, so it's really just a linear transformation. Now, of course, this also helps compute the eigenvalues, okay, because, well, hopefully you can, if you have a matrix A, you can choose a matrix B which is similar to it. This matrix B will be in a nicer form where you can read off the determinant of b minus lambda I quite easily. Okay, so this one example where this is true is if I take a triangular matrix. Okay, so remember this was a matrix with, well, it could be upper triangular, so these entries could be anything, and then anything below the middle, below the diagonal is 0, or lower triangular, everything above the diagonal is 0. In this case, the determinant of a minus lambda I, if this is a, is just the product of the diagonal terms, so a11 minus lambda, a22 minus lambda, up through a and n minus lambda. Well, and this is because, again, if I remove lambda I, then I'm getting that this is still an upper triangular or lower triangular matrix. And the determinant of a triangular matrix we saw was, by properties, the determinant just a product of its diagonal values. Okay, so therefore the roots of this are the a sub ii, so just the diagonal entries. So therefore the eigenvalues of a triangular matrix are just its diagonal entries. Okay, and again, any matrix that you can, that you can find a similar matrix which is in triangular form, then you can compute the eigenvalues. Okay, so for example, this tells you immediately that this rotation matrix is not similar to a triangular matrix over the real numbers. Right? So meaning if I have my matrices here, so if I write this as, this cannot be written as, P, T, P inverse, where this has real entries and this is triangular. On the other hand, it will turn out that if you allow the P to have complex entries, then you can even make this a diagonal matrix. And this is just one of the benefits of having more flexibility and allowing yourself complex numbers. So this also gives you some kind of amusing relations between the trace and the determinant. Eigenvalues, so the trace, so if you think about the triangular case, well, we have that the trace then is equal to the sum of the eigenvalues. Okay? And similarly, the determinant is equal to their product. So this is, at this point I haven't completely proven this, but this is again true by the fact that any matrix is similar to a triangular matrix. Triangular matrix. As long as, again, I'm willing to have these P and P inverse matrices be over C, but again, that doesn't change the eigenvalues at all. So both these facts are true with real entries, and you don't need the complex numbers to prove it. Like you can prove it without this fact, but that's kind of the simplest way to see it. Let me make one more remark, okay, which is that this determinant of a minus lambda I is called the characteristic polynomial of a. Okay, so we'll see this again shortly. Okay, and sometimes you put t here if you're thinking about it as a polynomial instead of lambda. Again, you can check from these two facts that since, well, the roots of this polynomial correspond to the eigenvalues, the determinant is always the constant term, and the trace is always the term before t to the n minus 1, as we saw in the 2 by 2 case. Okay, so now let's move to talk about diagonal matrices, okay, and diagonalization of matrices. So let's just first go with a special case. Okay, so suppose that T is a linear transformation T from V to V. Again, I'm thinking of this as just over F at this point. At some point I'm going to have to choose complex numbers. Okay? And suppose V has a basis of eigenvectors. Okay, they might have the same value. This is okay, right? Well then, certainly there is a basis for V, namely the basis of eigenvectors, where T is represented by a diagonal matrix. Okay, you just choose the basis of eigenvectors and you're getting exactly so the eigenvalues along the diagonal and zeros everywhere else. Okay, so in particular, any other matrix representing T is similar to a diagonal matrix. Okay, so maybe I'll say this is matrix A, so A is equal to S, D, S inverse. Here, what's kind of useful to know is that, well, the values here correspond to eigenvalues. Right, so the diagonal terms are the eigenvalues, and the entries here, so the column entries, are just the eigenvectors. Okay? Because the column vectors for S is exactly the linear transformation that takes the standard basis to the basis where this looks diagonal, but that basis is the basis of eigenvectors. Okay, so one case where this is kind of especially nice is where the eigenvalues are distinct. Okay, so remember, everything I've said about eigenvalues, I could just be looking at the identity matrix or the identity transformation and the eigenvalue 1, and every vector is an eigenvector. Okay, so you kind of get more interesting behavior and actually more nicely behaved behavior when you're allowed different eigenvalues. Okay, so let me say let lambda 1 be lambda r be distinct eigenvalues. Okay, and let's take their corresponding eigenvectors. Right now these have to also be distinct. Okay, then the vectors v1 up through vr are linearly independent. Okay, something that is clearly not true if you're allowed to take, well, if you start with the same eigenvalue, then these two eigenvectors could be multiples of each other or have some linear combination be 0. But in general, if you have distinct eigenvalues, you're closer to getting a basis of eigenvectors. There still might not be enough in general to span the vector space. At least you're not finding vectors that aren't going to form a basis because they're not linearly independent. Okay, so let me prove this. Okay, so how do we prove it? Well, suppose there's a linear combination, right, that's equal to 0. So we have alpha 1 v1 plus alpha r vr is equal to 0. Okay, and we can assume that this one is not equal to 0. Okay, otherwise it just gets chopped off and we start at VR minus 1, and then we'd be done by induction on the size of, or the number of eigenvalues. Okay, so we know that VR is an eigenvalue, or an eigenvector. So in particular, it's in the kernel of A minus lambda Ri, right? Well, so let's just hit this with the matrix, right? So we take A minus lambda Ri and apply it to alpha 1 V1 up through alpha R VR, okay? So what do we get? Well, we know that this has to equal 0, right? Because this whole vector equals 0. On the other hand, this is just equal to A minus lambda R times alpha 1 V1, or applied to it, plus all the way up to A minus lambda R alpha R VR. Okay, so this is equal to 0. This term is equal to 0 because this is a lambda rth eigenvalue. On the other hand, all of the other vectors, so the other terms, are eigenvalues, or have corresponding eigenvalues which are distinct from the lambda r. So what you see is that this is equal to alpha 1, lambda 1 minus lambda r v1, all the way up to lambda r minus 1, alpha 1 minus, alpha r minus 1 minus lambda r v r minus 1, and we get that this is 0. On the other hand, by induction, we can assume that the v1 through vr plus minus 1 are linearly independent. Okay, so by induction, we can assume that the v1 up through vr minus 1 are linearly independent, and what this means here, since we have a sum being equal to 0, all of the coefficients have to be equal to 0. On the other hand, since the lambda 1 minus, or lambda I minus lambda r are never equal to 0, we must have that alpha I is equal to 0 for all I. Okay, and now this is a contradiction because the equation then reads alpha r VR is equal to 0, and VR is assumed to be a non-zero vector, okay? And alpha r is assumed to not be 0. Okay, so therefore, we get that this is, so the v1 up through VR are linearly independent. Okay, so as a corollary of this, kind of an important corollary, we have the following. So if t from v to v is a linear transformation, okay, and there are exactly the number of eigenvalues, distinct eigenvalues, is equal to the dimension of v. So, okay, so there exists dim v distinct eigenvalues, lambda I, okay, then t is represented by the matrix lambda 1 up through lambda dim v, okay? So therefore, any other matrix representing t is similar to a diagonal one. Okay, so any other matrix representing t is similar to a diagonal, or is diagonalizable. Okay, and notice this statement does not depend on the field at all. Okay, so this is for, there's no difference between R and C actually, and you can just work completely generally, so this is true for any field F. Okay, so before going on to a couple other topics, I want to give the following theorem, which I'm not going to prove for you, okay? But it will essentially summarize the difference between working with the real numbers and working with the complex numbers. Okay, so if you have a real n by n matrix, well, then we know by the above corollary that it is similar to a diagonal matrix if and only if there are n real eigenvalues. Okay, so, and they have to be distinct. So essentially this, the converse of this statement is true. So I'll just say a real n by n matrix is diagonalizable. Okay, which means that it can be written as, so I'll just call this A. So A is P, D, P inverse, where P, D, and P inverse are in n by n matrices, and D is diagonal. Okay, so just the situation as in the above corollary. So this is true if and only if. First, A is equal to, I'll just say Q, D prime, Q inverse, where now Q, D prime, and Q inverse are in complex matrices, and the eigenvalues of A are all real. Okay, so you have to be able to diagonalize over the complex matrices, and you need all real eigenvalues. In that case, you could actually have chosen your diagonalizing matrices to be, with real coefficients rather than complex ones. Okay, so let's see some examples of this theorem in action. Okay, so one example is that, for certain matrices that we've seen, we can have no hope of diagonalizing them, even if we want to work over the complex numbers. So if I take 1n, 0, 1, this is not diagonalizable even over the complex numbers. Well, if it were, the only eigenvalues it has is just 1, right? So the only eigenvalues are 1. And so the only options would be 1, 0, 0, 0, 1, 1, 0, 0, and so on. Oops, 0, 0, 0, 1. Okay, and these are all easy to rule out. That's easy to see it can't be similar to any of these, and therefore just is not diagonalizable even over the complex numbers. For another example, let's go back to this rotation matrix that we saw. So we have cosine theta, sine theta, minus sine theta. Okay, so computing the characteristic polynomial will give you that the eigenvalues, okay, so the determinant of a minus lambda I are just e to the I theta, okay, or plus or minus. Okay, so when we think of this as an operator from R2 to itself, some linear transformation, we don't see any of the eigenvalues, but since they're complex, unless we're in a very special case. However, when we get complex eigenvalues, now when we view this as a linear transformation from C2 to C2, we now pick up the eigenvectors, and of course we'd like to know what those are, right? So we know that this is similar to a matrix E to the I theta, E to the minus I theta. Okay, so now to work out the eigenvectors, well, we're looking at things in the kernel of A minus lambda I, okay? In this case, this is equal to, so this is cosine theta plus I sine theta, that's e to the I theta. Okay, so we get minus I to the sine theta, minus sine theta, minus I to the sine theta, and we're looking at the kernel here. And now notice that this first row is just I times the second row. Or sorry, I times this row is the second row. I times row 1 is equal to row 2. In particular, we can multiply, we can add that to cancel row 2, and then divide by sine theta. So you can do row operations to get to, let's see, 1 minus I, 0, 0. Okay, so therefore a vector in the kernel, well, so what this does is it sends WZ to W minus IZ 0. Vector in the kernel is of the form I1. It's easy to see that actually any vector in the kernel is spanned by this. So the kernel looks like I1Z for Z in the complex numbers. And so that's one eigenvector, okay, so or set of eigenvectors. It looks like this. And the other one, so vector or vectors in the kernel of A minus lambda prime I, okay, for the other, for e to the minus I theta instead of e to the I theta, is equal to a multiple of minus I1z. Okay? So therefore, so these are your two collections of eigenvectors corresponding to these two eigenvalues. Okay, so if you want, you can now write down the matrix, which takes in this rotation matrix and puts it into this diagonal form. Okay. Okay. So in this lecture, I think I'm gonna do one more topic, okay, which is called the Cayley-Hamilton theorem. Okay. So let me say the statement of it. So recall that we're looking at the determinant of A minus lambda I, okay, for now A just some n by n matrix, and now this was its characteristic polynomial. And I said, well, actually it turns out to be, so it's a polynomial of degree n, actually turns out to be a monic polynomial, so it looks like lambda plus a n minus 1 lambda to the n minus 1, all the way down to a1 lambda plus a naught, where these ai, well, they're in your field. Okay, so let's just say real or complex numbers. And now what we can do is plug in a into this equation. Okay, so in other words, and maybe I'll just call this P of lambda, okay? Or maybe PA of lambda. So now we can plug A in, meaning, I mean, lambda is a real number, but you can just pretend that you can plug matrices in, right? We're very comfortable now with raising matrices to nth powers. Okay? So I can take something like A to the n plus an minus 1a to the n minus 1, all the way up to a1a plus a naught. And now, of course, now for this to make sense, I can't look at this as a constant. I have to look at it as a matrix, right? These are all matrices. So the way I fix that is I just say this is a naught times the identity, okay? N by n identity. And now the theorem, so now this is the Cayley-Hamilton theorem, is that this expression is equal to 0. Okay? So in other words, the formula, when you're looking at this polynomial and solving for eigenvalues, so A solves the polynomial, which computes A's eigenvalues. Okay? Kind of a strange but remarkable theorem, I'd say. So let me give you the example, which I won't prove in general, but you can just compute, at least in low-dimensional cases. So in the 2x2 case, let's just see what this looks like. Well, we saw that the determinant for an A, if I take A to be in general 2x2 matrix, and this characteristic polynomial, I guess I'll call this A, so PA of lambda was equal to lambda squared minus the trace of A times lambda plus the determinant. Okay, so what the Cayley-Hamilton theorem is stating is that ABCD squared minus the trace of A times ABCD. And again, this is just, so this is A plus D, and what you're doing is multiplying this by each of the coefficients, or multiplying each of the coefficients by the trace, better way to say it. And then plus, I'll just say here the matrix AD minus BC, 0, 0, AD minus BC. Okay? The claim is that this is equal to 0, 0, 0, 0, which, again, in this case, you can just compute. Okay? And then in general, you can imagine this determinant formula is getting much more complicated, but it's kind of nice that you can just plug this in and you'll get some relation between the powers of this matrix. Okay, so for 3 by 3 and for general n by n, this relationship is much more complicated since the characteristic polynomial is more complicated. Let me give you a sample application, or maybe I'll give you 2 applications here. So here's one sample application, is if you take A to be any n by n matrix, and let's say that it's strictly upper triangular, okay? So what this means is that there's zeros along the diagonal and zeros below. Okay, so a good one would be like ABC 0, 0, 0, 0, 0, 0. Okay? And let's just say this is n by n. Then the Cayley-Hamilton theorem says that a power of this matrix has to be 0. Okay, so it says A to the n is equal to 0. Of course, it might be a lower power depending on what the matrix is. Okay, but certainly if you raise it to the nth power, you'll get 0. And the reason is that, well, what's the characteristic polynomial? Well, you're looking at the determinant of A minus lambda I. This is now an upper triangular matrix. Okay? So the characteristic polynomial of lambda is just lambda, or negative lambda, to the n. Okay? And what this is saying is that when you plug in A as a matrix, you get 0. So this is negative A to the n, and you get 0. On the other hand, this also just implies that A to the n is 0, right? You're just multiplying it by plus or minus 1. If it's 0, then A to the n was also 0. Okay, so since I guess we're at the 53-minute mark here, I'm going to just go to the proof, give some ideas here. Okay, and there's actually a couple proofs. I'm going to present ideas from both. But in both cases, or the first thing to note, that this theorem, so Cayley-Hamilton theorem, is true for diagonal matrices. Okay, so if I give you a matrix A1 up through AN, 0 is outside of the diagonal, and I'm looking at, so this is A, I'm looking at the determinant of A minus lambda I, okay, then what I'm getting is A1 minus lambda up through AN minus lambda. Taking the determinant here, product of the diagonal terms, and now when you actually plug in the matrix A into this, it's easy to see that this solves the equation. Okay, so this is not hard to show, and it's on the homework. It's also true for diagonalizable matrices. Okay, so if A was just similar on a matrix, it would also satisfy this equation. We've already seen before that similar matrices have the same exact characteristic polynomial, and you can check that if you plug in A and it solves this characteristic polynomial equation, then and you plug in, you know, PAP inverse, then it will also satisfy that equation. Okay? So that's good. So we're already at a pretty good start in the sense that we've gotten to all matrices which can, you know, in some basis look like a diagonal matrix. Okay, so here's the new fun idea, okay, which is that any n by n matrix is arbitrarily close to a diagonalizable matrix. Okay, so this is usually called the diagonalizable matrices are dense in the space of matrices. So this is the first good example that we've seen in this class of where analysis will really help us prove a non-trivial theorem. Okay. So what I mean by this is that we can wiggle, I'm being kind of vague, wiggle every entry by less than epsilon, okay, and this will make n distinct eigenvalues. Okay, so the reason you should believe this, and again, so I should say this is diagonalizable over the complex numbers, right? So the reason you should believe this is that you're asking a polynomial, namely determinant of a minus lambda I, to have n distinct roots. Okay, so you have some polynomial, I'll just say p of lambda now, so it's lambda to the n, up to lambda to the n minus 1, all the way up to a naught, okay? And what you want to rule out is polynomials with multiple roots. But a polynomial to have multiple roots is a very delicate condition, okay? So p having multiple roots, so here I mean having a root raised to some power is quite delicate, okay? And if you essentially take any little wiggling of the coefficients of this polynomial, it won't happen. So you can see this in the case of degree 2, right, very simply. So if I had p of lambda is lambda squared plus b lambda plus c, okay, maybe I'll put a here. This is just true for polynomials. Then the condition that there's only one root is exactly b squared minus 4ac is equal to 0, right? But notice this is quite, an exact procedure, right? You need to exactly hit 0. So if I look at like b plus epsilon squared minus 4ac, well, it won't be 0, and I'll have two distinct roots. Okay, they might be complex if I kind of pushed it to be less than 0, but it will certainly not be equal to 0. Okay, and I can modify a and c as well. So that's the general idea, which I won't give, too much more details there, but you should think it's very hard to be non-diagonalizable over the complex numbers. You really have to have this characteristic polynomial having a root that's a multiple root, and that's hard to find. Okay? So therefore, we can find matrices, let's just call them AK, okay? So that the entries of AK converge to the entries of A, okay? And the AK are diagonalizable, and therefore satisfy Cayley-Hamilton. Okay, but now we have this polynomial, which we call PA of AK is 0 for all k. The AK, the entries of the matrices AK converge to the entries for A. This implies that the polynomial when you plug in A is 0. Right? Here you're definitely using some things like polynomials are continuous. Okay, so you have, and this is just some kind of methods for analysis that you have to use, but that's the proof. Okay, so if you can prove it for diagonal matrices or diagonalizable, then you're approximating your matrix by those. You're plugging it into a continuous function. It's going to have the same value as the things that we're approximating it. Okay, so that's the proof. I think I will give one more proof of this theorem at the beginning of the next lecture, but since we're already over the hour mark, I'll just say thanks.